Okay, so I left here that I said I want to combine these two equations by eliminating h between them, assuming that b h over theta and p q over theta. And now you can, for example, divide this by theta and then add it to that equation which has h over theta, or you can multiply this by theta and then add it to this. Let's do that. We multiply this by theta and add it to the energy equation. So you get rho dE dt plus minus TKL VKL minus QKK minus rho H. But then you notice that, okay, let's just do that. It would be equal to plus rho theta ds dt minus rho minus theta and then qk over theta k and finally minus rho h over theta, and this must be equal to rho theta a. And I had to subtract them from each other, so I put a minus sign here, a plus sign here, a plus sign here, and a plus sign. And this was to be multiplied by theta. So you can see that these two thetas cancel. You have minus rho h plus rho h. They cancel each other. And from this term also, you get a 1 over theta times qk, and that cancels this plus qk. So from here only remains the qk times derivative of 1 over theta, and that's minus 1 over theta squared derivative of theta. So if you put all this together, you get minus rho dE dt, and then plus rho theta ds dt plus TKL VKL, and then minus 1 over theta Q K gradient of theta, and finally all of this should be equal to rho theta gamma, and this must be non-negative. Did I do it right? I think I have all the terms. This is coming from here, that's coming from here, that's from here. This qk together with the other one gives me only this term, and that's it. Then I noticed that, because you know, we like to have everything in terms of the independent variables. You remember the gradient of theta, the derivative of theta, the gradient of velocity. So I will also here put this theta in there, becomes theta s, and then I will have to use the product rule to subtract from it the time derivative of theta. So if I do that, I will then get minus rho ddt of E minus theta s, and then minus rho s d theta dt, and then plus KL VKL, there is a comma here, minus 1 over theta QK theta K. I apologize for my handwriting. So I hope you get to agree that this is, and I did this, what you find interesting, I find interesting that you have this combination here appearing as a result of this operation. And in fact, many of you may recognize this. This is Helmholtz free energy. So it just came out as a result of this derivation. I didn't throw it in. It says that this combination always appears together in the production of entropy. So I get therefore this equation now as the final result, where A is defined to be the Helmholtz free energy is defined to be internal energy minus temperature times internal entropy. Okay? So now I have this entropy inequality and I have these constitutive equations. Remember, I came to these constitutive equations from a very general description saying that my effects are functionals of motion, the gradient of motion, the temperature, gradient of temperature, time rate of change of motion, and so forth and so forth. And through those axioms, I only limited myself to the first derivatives. And I also throw away the derivative of motion, which is velocity gradient. I didn't include it here. Just see what we get. I could include them. It's just a much simpler set. See what we get. Now, and this must not violate Balance law and must not violate the entropy inequality. What does it mean? That means that the ADT, if you substitute in here, you get all kinds of derivatives of this argument. So we need to do that. T is given by this functional, whatever it is. If you put that in here, together with these derivatives and this and that, must still remain non-negative. So we do that. Now, the operation we need to do is just take the time derivative of A, and the time derivative of A is therefore chain rule of differentiation with this, and I see that there is a dEKL dt, and by definitions that I had earlier, that the velocity is the time rate of change of displacement, this can be shown to reduce to the deformation rate tensor multiplying the gradients of displacement. So I use this in here and I put everything back in my entropy inequality. By the way, one thing I forgot to emphasize, and that is here. Remember, this is a constitutive equation and these are my independent variables. And none of you asked, well, temperature and the temperature gradient, they are not independent, or are they?
Well, at one point they are independent.
Yeah, in the experiment, you can vary them independent.
If there is one realization, so I have my material, I have some initial conditions, I have boundary conditions. For that situation, I get the temperature field. And for that temperature field, I know temperature gradient everywhere. But that's one realization. I have a zillion thermodynamic states possible, and those zillion thermodynamic states, at every point, you can have a temperature and you can have a temperature gradient for this kind of particular state. Another realization, different initial, different boundary condition, you can have another different temperature gradient. Is that acceptable? So we are looking at a set of governing equations, conservation laws, constitutive equations that are valid for all thermodynamic states of a given material. And then for all thermodynamic states, at any given point, temperature and temperature gradient are independent. You can have for a given temperature gradient, for a given temperature, you can have many temperature gradients. Here's an example. If I have a rod, for example, and this rod I subjected through some initial conditions and some boundary conditions, I subjected to a temperature gradient, and the temperature gradient looks like this. Now, this is one experiment. I do another experiment, and I subjected, and this is steady state. So you have the steady state conditions, I keep the boundary temperatures, and that's the steady state. Now I change the initial conditions and boundary conditions, and I get this as my final state. Now, at this point, I have the same temperature, but I have different temperature gradients. Because these are two different thermodynamics. And I can have it the other way. I can have it a zillion ways. So temperature and temperature gradients are two independent variables. And that's why we have them here as independent variables. Any time derivative or a spatial derivative of a quantity is not the same as related to that quantity itself. Okay, so with that, I substitute all of this in the entropy inequality, and I get this as my expanded entropy inequality. Note that I have grouped terms together. For example, these are multiplying d theta dt. So I put them all together. These are multiplying dkl. And this is the time derivative of theta k because I have it here. And this is the term that I originally had, the entropy inequality. Now, why do I do this? For various reasons. One thing I should really immediately realize is very interesting is that, remember, A is a function of these variables. So is S, so is temp, because we have everything was, all effects were function of these variables. So this term is independent of d theta dt. There is no d theta dt in this term, is there? There is no d theta dt here, and here, and here, and here. So in this expression, this production, net production rate, is a linear function of d theta dt. And also, in fact, a linear function of this, because this dkl is not in my list of independent variables. I chose that, and the same with this. So that's very interesting. These are all appearing linearly, and these are all not functions of it, and that's therefore gamma is linear. What does it tell me? What does anyone mathematics will tell us? For this inequality to be valid for all possible numbers, d theta dt can be a large positive number, could be a large negative number. I start initial condition and boundary conditions such that I get a huge temperature time derivative, or a huge this or that. So they can be, for all thermodynamic states, and for all thermodynamic states, d theta dt can be large negative or large positive number. Which means that potentially I can create a situation where this is negative, this is positive, or even maybe zero, and that means the entropy production rate will be negative. That's not allowed by second law. We must exclude any possibility. No process will occur for which entropy inequality becomes negative. So we must exclude those.
Excuse me, I might have misunderstood something fundamental, but if you go back to the previous slide,
This one?
yes, derivative of Helmholtz with respect to temperature in the next, in the bottom, second to bottom equation.
This one?
No, it's in second to bottom.
Oh, here.
Yes. Isn't that identically equal to the negative the entropy?
Why should it?
Term will be zero.
Why should it?
Well, isn't that the definition of with the relation?
Not as far as I know. I started with my molecular picture
Right.
yesterday. I derived conservation laws. There was nothing to say S must be minus dA dt.
Okay.
Then I started with these constitutive equations, where I said the effects are a function of temperature and motion of all points, all pastimes. There is nothing there saying that.
Okay.
Then I reduced that to this simpler. Still, there is nothing to require that.
But you did identify the A by E minus TS.
Okay.
Meaning that there is some implicit construction here that the A, the derivative has no condition.
Right. No, but the derivative is this. I defined
the condition.
A
Under
is
certain condition that I agree with Magnus.
The only condition, as far as I know, at this stage, I said this is a function of EKL, theta, and theta k. This is a function of that. Therefore, A is a function of EKL, theta. That's the only condition I have to.
So it
No.
is a different Helmholtz energy than in the normal.
No, it's not. I don't have any normal. I don't
Yeah, you-
have all the information you have because of your experiences or whatever.
Yeah.
I have my own world of conservation laws.
But an alternative definition of the entropy is dA dt.
No,
At
that
constant
is a
volume.
constitutive.
At constant
I'm going to
volume.
derive it actually.
Uh-huh.
You start with it. I don't want to start with it. I derive it. Just
Yeah,
bear
that
with me
is
1
the
minute.
difference.
Okay. At this moment, S is not minus the ADT. Not that I do not believe it. Prove it to me. And I'm going to prove it to you that it must be. Prove it is different than you. Yeah, that's I was told.
It's a
Gibbs
different
told
set
me.
of axioms.
Is it the equilibrium condition that you're lacking?
No, it's actually valid all conditions, non-equal.
No, but I mean that relation comes from.
That comes from equilibrium thermodynamics.
Yeah.
Yeah, but let's derive it. Why should I accept Gibbs? He was a genius, but I like to derive things. All right, so let's do that. So at this stage, there is no such an assumption needed. I don't need it. The only thing is I follow mathematics and my physical axioms that I hope you agreed with them. So the only thing is that I need to have these coefficients to be zero identically to ensure that there is no thermodynamic state that tells me entropy inequality becomes negative. There is no material that happens for it, therefore they must be zero, and now I get S is equal to minus the ADT, because one of them is this. So these must be zero, this must be zero, this must be zero, and this must be non-negative. It's a mathematical result. And so I get, indeed, oh yeah, you're right. S is minus the 18. Okay? And moreover,
But there is no condition V on this last equation, which means that it is not the same as a normal definition.
why is it not the same?
S
A is minus E minus theta S. That was the definition, that's how I got it. Actually, I didn't have A in my conservation laws. It just appeared naturally as a result of my operations. And I found extra that, oh, then S is related to A by this relationship. It's a derived result. I didn't assume anything.
No, I see that,
You-
and
you
you have
should-
your definition of S then here.
My definition of S,
May not be Boltzmann definition, because that is linked to another differential, namely the one
but
with.
outside entropy, internal entropy is always the derivative of.
Yes, but at constant volume, I think.
Oh, this is indeed at constant EKL. Remember, this is a partial derivative.
Yes.
This is at constant EKL. That means indeed no motion, no volumetric change.
Okay.
These are partial derivatives. I'm sorry, I didn't make that clear. Because A is a function of motion and temperature gradient. So actually, I guess it's also adiabatically. Temperature gradient must be constant too. Then I get that stress tensor. Oh yeah, so A also cannot be a function of temperature gradient. So now that means A is only a function of EKL and theta. It's not permitted to be a function of temperature gradient. I also find that the stress tensor is related to the derivative of A with temperature at constant temperature, with motion, with the strain tensor at constant temperature, because this is partial derivative.
And now it depends on x sub k.
Everything depends on X.
But in your
If it is
expression
heterogeneous,
in the expression for the time derivative of A, you did not get the contribution.
no, because dx dt is 0. X is the material time derivative, and the X is the material coordinate, and the time derivative, material time derivative of X is 0. That's, you're right. I mean, I should have been more careful. Yeah, I should have here, just to make sure that others also, here I have always an X. I have been not careful.
Yeah.
I'm not a mathematician, I'm sorry.
No.
Mathematicians are more careful. So there is an X here, and then there is a dx dt, which is 0. Okay, so actually I am almost done with what I call the exploitation of the entropy inequality. I started with some general constitutive equations for A, S, T, and Q, and I came to the result that A must be a function of this, S must be related to that, a stress tensor must be related to this, but these are still some general dependencies. It's not specific enough to solve problems. We have to have specific relationships. One way to do that is says, okay, my material behaves linearly in terms of a stress-strain relationship. Okay, so I'm going to assume a linear, derive a linear relationship for TKL, and I do that by expanding A in terms of EKL, and then leaving out some higher order terms. So I do that by saying, okay, by saying that I write this in a second order, and then I neglect the higher order terms. If I do that, then I also, by the way, do that for the heat vector. The heat vector is a function of these, so I do that as well. I do not expand in terms of temperature. I only expanded in terms of EKL. So that means all these coefficients are still functions of temperature. So if I do that for A, that gives me a linear relationship for a stress tensor. If I write that for a small deformation, then basically I get, here is a constant. For a small deformation, these are the unity. So I get here a constant, and I get here a fourth rank tensor multiplying the strain tensor. This is because it's the derivative of change of energy with motion, second derivative of it. So, which means that the stress tensor has some initial state of stress plus whatever you get as a result of deformation. We can always set initial state of stress to 0. So if I have this material and I want to put it under motion, I can assume that, okay, stress tensor is 0 here everywhere. And then I deform it, I get extra. So you're allowed to do that. In other words, you work with T minus T0, because in all equations you have gradients, so that will be 0. Okay, so this is a linear relationship. This is actually Hooke's law of elasticity in its most general form. And if you have an isotropic solid, now you can have all kinds of isotropy. If you have a fully isotropic solid, then this must be also a fully isotropic tensor. The most general form of a fourth order isotropic tensor is a combination of the canonical deltas, the unit tensors, and then with coefficients. These coefficients are functions of temperature. And if you put this back into here, given the fact that the stress tensor is also symmetric and the strain tensor is symmetric, we will be left with only two independent coefficients that is given here. So this is the Young's, these are Young's Laplace, Young's moduli, the linear elasticity isotropic material. Okay? Yes.
Can we get irreversible deformation from as well?
Irreversible?
Irreversible deformation, I mean plastic deformation.
No, not in this fashion. This is elastic, linear, therefore it's reversible.
Can we add something to this kind of methodology to end up with plastic formulation?
Definitely. So what you are saying is what I suggested earlier. I develop some equations, I give them to you, and you say, yeah, this is reversible. I don't get reversibility. Fine, we go back to our original set of independent variable we chose. We have to add something there to account for this extra complication. And there are various ways you can model plasticity. One of them would be to add deformation rate tensor. Then becomes viscoplastic, viscoelastic. Because then you add viscosity, or this sort of plasticity. Then you will see that you get viscosity in there, and then you will have indeed, and in fact you will see that you get this only at equilibrium. A non-equilibrium, then there is more movement, then you get extra terms related to plasticity. But that's the whole idea. It's such a systematic fashion that we should always go back to the drawing board and see, okay, what is it that missing there? Okay, I'll do that for a couple of other examples. So you can also look at what we call the residual entropy inequality, because you remember all the other terms were zero and only this survived. I think I'm missing a minus sign here. And then what we do then is define when is this net production zero. We call that equilibrium, when the net production of entropy is zero. And we notice that if theta k is zero, then gamma will be zero. And we define that equilibrium. So we define equilibrium to be when there is no temperature gradient. Now, at equilibrium, gamma will be at its absolute minimum, because we have constructed everything that gamma is always non-negative. The minimum value it can have is zero. So it is at absolute minimum. If it is at absolute minimum, that means under these conditions, the derivative of gamma with this variable must be zero. And the second derivative must be positive definite to be minimum. So we then get these requirements. These are absolute mathematical requirements, that this must be zero and this must be positive semi-definite. Now the first one will tell us that heat vector must be zero at equilibrium. Yes.
I'm sorry, I haven't attended the course from the beginning.
Oh.
But I understand the gamma is the entropy production, right?
Is the net rate of entropy production.
Right. So, can you comment on the what Prigozhin said, that at a steady state you have a minimum entropy production? At equilibrium it's zero.
Yeah.
Which is
Okay.
the absolute minimum.
Yeah.
But what about if you have a steady state process compared to a transient process?
Yeah, so it depends on what you mean, which kind of material you are studying. In case of the solid, if you go back to the constitutive equations I started with, I said that my material behavior, stress tensor, heat vector, they only depend on deformation, temperature, and temperature gradient. So a steady state is the same as equilibrium, because, in other words, if the deformation rate gradient is zero, that's a steady state, the deformation rate gradient being zero, then everything still holds. For a solid, I cannot make a distinction between a steady state, and I assume by steady state you mean steady state motion.
Well, any
Or you mean
process.
thermal?
For example, thermal, yes.
Yeah.
What about if you have it's not deformed, but you have a heat flux through these?
Yeah, I don't see why that should be
Then you have
entropy
a
inequality. I don't see why entropy inequality production should be zero.
No, it's not zero. But
Oh, okay.
But it's at a minimum value compared to a transient heat
Oh,
flux.
could be, but it's not absolute minimum.
No, that's right.
Okay, no, you're right. No, I'm sorry. So now here, the only restriction I'm following is that it will be absolute minimum.
Okay.
And then it is only at absolute minimum that I must have this requirement. That means that for the entropy inequality, entropy production rate to be at this absolute minimum, this must be zero, which if you look at gamma was qk times this, so then qk must be zero. There must be no heat flux at equilibrium, thermal equilibrium condition. And moreover, this second derivative must be positive, which means that the derivative of qk with temperature must be positive.
And I disagree with that.
Which part?
B, because it could well be zero.
But it's not absolute minimum.
Of course, it is an absolute minimum if you take the force order derivative to be positive and you take all earlier derivatives to be zero. The second and the third, but the fourth order is positive semi-definite.
But when means derivative, here I am not, the only thing I have is qk is a function of temperature gradient. I don't have any derivatives.
I mean, so why do you have a derivative with respect to the temperature?
Okay. Because,
Yeah.
let me write this here. Okay, let me, just 1 minute. This is not,
Yeah. So
because rho theta gamma is equal to qk
Yeah.
theta k.
I understand.
This-
So you take qk.
What are the fourth derivative? I don't have any fourth derivative.
qk is the heat flux.
Correct.
Right? You take it a constant times the third power of the gradient.
Okay, you could do
That
that.
satisfies your equation, and it doesn't satisfy B.
No, but, okay, let's do that. Let's do that.
Yeah.
See, at this stage, I am not proposing anything in terms of how nonlinearity is. Actually.
Well, I mean, you are going to conclude from B that Q is linear in the
I'm
gradient.
not, no, I'm not concluding that, absolutely not.
Oh, well,
Oh, I'm
that's-
sorry, no.
That's it.
I'm not concluding that.
Never-
The only thing it is telling me, this must be positive definite. Whatever the
Yeah,
relationship,
So that means that it can be zero.
this must be zero, doesn't have
It
to.
can be zero. Positive
Yeah.
semi-definite means larger than or equal to zero, so it can be zero.
It could be zero too, yeah. Well, no, why should it be zero? No, I don't, not exactly not. In fact, positive semi-definite, it doesn't have, to, it doesn't, must not be zero. That's what
In
it
that
is.
case, it is positive and not positive semi-definite.
I'm not sure.
It's
I
just the
don't know.
mathematical meaning of the word, right?
Is it?
Positive semi-definite
Are you
means larger than or equal to zero.
That is not my understanding, but because I copied this from Harringen and Tuesday. So
So they are right, so it is positive or zero.
you're saying that I should remove the semi.
Also, yeah, if you
Let's check that together.
If you
This is in
remove
the rational thermodynamics literature.
If you remove the semi, I disagree with the statement.
So what do you want to remove? The whole thing?
I don't want to remove anything. The statement there is correct.
Yeah,
And
positive
it implies that it can be zero.
No, I don't want it to be zero.
Positive semi-definite, it means larger than zero.
Yeah.
It's not zero.
It cannot equal
Or
to
you
zero.
will be linear.
That's what I
It will be
understand.
linear.
If you wanted to include zero, you would say non-negative, right?
Maybe, I mean, that's
No.
Well, I mean, the entropy production is positive semi-definite.
No, entropy production is non-negative.
That's rubbish. In equilibrium, it's zero, right? So, I mean, it...
So non-negative, that means also
Oh,
zero?
no, the mistake. It's larger or equal to zero.
yeah.
Okay.
Yeah.
Look, we will check this together
Okay,
with
yeah.
Truesdale.
Positive definite means larger than zero strictly.
So I don't know why the semi-definite,
Yeah,
it's in the literature.
Truesdale is usually...
But what I want this to be positive. And I thought semi-definite comes for tensorial quantities actually, but I'm not sure. But this must be positive. It's not zero.
Well, I disagree with that. That doesn't follow from your equation.
No, look, for a function to be at absolute minimum, it means that it should be curving upwards.
Sure, so...
And that means the second derivative must be positive.
x to the power 4 curves upwards.
Yeah, and then it's...
So, and that is, in that case,
Yeah, but
the second derivative is zero.
No, only at x equal to zero.
Yeah, but that's where we are talking about, right? I mean, that's equilibrium.
Yeah. I don't know.
Well, let's
This
continue and-
is the exact wording I have copied from the letter. I must say, I admit that I have made a mistake.
No. I think that is perfectly correct what Truesdale says. Yeah.
Okay.
Yeah.
Then this will give me that qk at equilibrium must be zero, and its derivative must be therefore positive, and which means that if I make a linear approximation, and if you want we can do a third order approximation, that so a linear approximation means that qk is equal to some constant plus a tensor, sorry, k, a constant k, and then a tensor times derivative of temperature, that first of all this must be zero, secondly this kappa kl must be positive. And you don't like that to be positive?
It's positive semi-definite.
No, but isn't this a discussion sort of, on one side you are working within a linearized framework, and within a linearized framework this is absolutely true everything, but if you include also non-linear terms, higher order terms,
Okay, let's do that.
then of course.
So I add here a plus kappa KLM theta L theta M. One more term?
Well, yeah, this term you can forget about. Is the next order term that is the
Plus K L M N theta L theta M theta K theta M.
Yeah.
Now this term must be zero because there is no third order isotropic tensor.
Yeah, exactly.
But this one, if you take its derivative with theta, that gives you derivative with theta k, that gives you k kappa k l m n, and then theta l theta m, the second derivative. No, the first derivative, sorry. The theta, and then that's it, right?
The first derivative is respect to what?
Theta k. See,
Yeah. That's,
the first derivative with respect to theta l. And then at equilibrium. And at equilibrium, all those thetas are zero. So actually becomes zero, you're right.
yeah.
That becomes zero.
Yeah, exactly. Yeah.
Okay?
But yeah, I mean the reason I bring it up is that I dispute that the equation leads to a linear relation. That is
No, the
something
equation absolutely does not lead to a linear
we-
relation.
Exactly.
I say if I have a linear relation, what does it give me?
Sure, in that case.
Yeah, I'm not saying it requires, the entropy inequality as given here, what I call the residual entropy inequality, does not require a linear relationship.
No, I think it
Yeah,
may be
I
the
fully
same
agree.
power. Yeah.
No, it can be any. The only thing is that whatever you select for k,
It has to
you
be-
must be substitute here, and then it must satisfy this.
Sure, sure, sure.
Which means that at equilibrium it must be 0, the k, and the second derivative, the derivative of q with respect to must be positive, semi-definite.
Positive semi-definite.
Semi-definite. Okay, I think you tried to confuse me and you managed. Very good. All right, so this was for a solid. So I hope that I can quickly go through. How about, well, that it was a solid, I didn't have to say that in the beginning. Only after I derived the equations, you could see that my equations are now such that I have heat transfer, so it's a heat conducting material, and the linear relationship says that the stress tensor is proportional to the strain tensor. So that's what we call. Then somebody tells me, oh, I know this is elastic solid. So okay, perfect. So I develop something that's useful to someone. That's the idea. You could have gone the other way around, and like you're saying that, yeah, I also have something that's viscoelastic. Then I say, okay, let's go sit together. What are the state variables? I put them in my constitutive equation, and indeed that's. So we could do that here, for example. Say, look, I'm interested in a non-viscous fluid. And say, okay, for a non-viscous fluid, I have the balance laws. That's always given. I have the entropy inequality. And then for the constitutive equations, instead of this full setup, and actually it's not full, as you know, I said earlier, you have higher orders of these you can include. But for a non-viscous fluid, I know that deformation doesn't. You can deform a gas anywhere you want. It doesn't mean it does anything. It can take the shape of the container under the same conditions. So EKL has no influence on effects. The same for VKK. The velocity gradient in gases, you can have them and doesn't matter. Gas can move faster here and slower here. That's not causing any, we're talking about non-viscous gas. So that means now I'm going to, oh, what is VK here doing? So there are two things I have to do now. First of all, I'm sorry, this is a paste and copy and paste problem. So I already explained that you cannot have a dependence on velocities and not an objective quantity. Okay, because the motion is not there anymore, rho has to be included, because you remember I said that rho, if you have rho 0, and if you have motion, you can find rho at any other time, where J is the determinant, the Jacobian of the motion. But now the motion is gone, is not playing a role, I have to include rho. So for a gas, the independent variables are rho, temperature, and theta k. From previous exercise, you could have noticed that if I do not include a dependence on the temperature gradient, that entropy inequality would require the heat flux to be 0 for all conditions. So that's a non-heat conducting material. But so if when I include it, then I'm allowing for heat conduction. So these are my independent variables. I put them into the entropy inequality. So dA dt gives you these three terms. And then I have to make sure conservation laws are not violated. To make sure that that is the case, from mass balance, I realize that d rho dt is related to the velocity gradient or the deformation rate tensor. So I must include that in here, otherwise I'll make wrong conclusions. So I put that in here, and I put everything back in the equation. If I do that, I get these terms in the entropy inequality. The term we had earlier. Now TKL plus the rate of change of energy with rho is here, multiplying DKL. All the red terms are appearing here linearly. None of these terms are functions of temperature time derivative or the gradient of temperature time derivative or DKL. So these are appearing linearly. For the entropy inequality to be valid for all thermodynamic processes, this must be 0 identically. And that gives me that, okay, for the material I was modeling, for this material, S must be minus the ADT, and the stress tensor must be an isotropic stress tensor. And at all times is equal to the time rate of change of free energy with density. This you recognize. What is this?
Pressure.
We call this pressure. We say fluid where the only state of stress is an isotropic state of stress, we call that pressure. That's our definition. So we find out that the equation of state is actually derived here because we define this as pressure and what is that? So pressure is equal to minus rho squared dA d rho. And remember, A is a function of rho and theta. It's not a function of the gradient of theta anymore. So pressure, therefore, is a function of rho and theta. And that's the equation of state. And assuming that there is a monotonic relationship, not assuming, based on experiences, then we can also invert this relationship and write rho as a function of pressure and temperature. That's allowed to.
I suppose that the second equation of state for the energy, the caloric equation of state, can also be derived from.
So that is when we go to saying A is a function of theta and S, and if you write a linear relationship for A as a function of theta, then we get indeed the equation of involving specific heat capacity and so on and so forth. Yeah. So at this stage, everything says, okay, it's a function of rho and theta. What function now? Then we have to choose. As I said, to really do problems in physics and engineering, we have to have a specific form. It's not enough to know this. That doesn't help. We have to have some specific form. Often we assume a linear relationship. Now, again, the entropy inequality is there. The residual entropy inequality, go through the definition of, these are results. The definition of equilibrium, theta k must be 0, therefore the entropy inequality is at absolute minimum. Now, all that we just did, you can derive in this fashion. So for a non-viscous fluid, we find that the stress tensor must be an isotropic state where it's defined like that. If you assume a linear relationship for Q, again, then we get, that the Q must be simply a coefficient kappa KL times temperature gradient. If we put all of that together, now we get this kind of relationship. Now this is the momentum equation for gases, energy equation, and indeed, if you assume linear relationship, you can then get the energy equation or the heat equation, basically. So this is for a non-viscous fluid. And then we can say, okay, how about a viscous fluid? Now, then we go back. In the case of gases, we didn't put this, and we got that the stress tensor is only an isotropic result. And it was because, I'm sorry, I have to go back. We got that a stress tensor must be an isotropic state of stress because this term, this was not in my set of constitutive equations. Forces this to be 0. If we don't want this to be 0, we say, okay, everything must depend on that as well. Then it's not linear anymore. And in fact, for non-viscous fluids, that's what we should do. And so if we include that, and now if we go to the entropy inequality and substitute here dA dt, now then dA dt has the rho dt in it, has this one in it, d theta dt and the derivative. For d rho dt, we substitute from mass balance. So if you put that there, and now if you put things together, this is not red anymore. Because this is a function of that, this is potentially a function of that, and all of this are functions of this. So the only requirement is that this must be 0, this must be 0, this must be 0, and then that sum is the residual entropy inequality. So we got always the result that A is only a function of rho and temperature, and in this case we find that, so though A is a function of temperature, and we find that this is the residual entropy inequality. Now, we define equilibrium to be the case that the stress deformation rate tensor is 0 and theta k is 0. If we define that to be the equilibrium state, that means the entropy production is 0, it's an absolute minimum, therefore the gradients of that with theta k and dkl must be 0. And now, you see, this is really a tensor because these gammas are various components of temperature gradient, there are 3, and various components of dkl, that are 6. So this is a, I don't know how many rank tensor. And that must be positive definite. And with that, we find that under equilibrium condition, there would be no heat flux. And under equilibrium condition, the stress tensor is isotropic state of stress, which is the case in fluids, viscous fluids. Under the equilibrium condition, if there is no movement, then we only have pressure as the only state of stress. And so that's again the definition of pressure coming up. And if we have a resume of all the results, yeah, these are what we have. Okay, so this was at equilibrium, we have this. How about non-equilibrium? Now, under non-equilibrium condition, the stress tensor is still a function of dkl, the deformation rate tensor. Now, and if you are interested to develop a linear relationship, which is now proposed here, and we say TKL is, no, this is the equilibrium part of it, and this is the non-equilibrium part of it. And the non-equilibrium part, I assume a linear relation with the deformation rate tensor and with the temperature gradient. Now, we can do the same for heat vector, is a linear combination of these. A fluid, we say a simple fluid is isotropic. If that is the case, that means a fluid behavior in different directions is the same. It doesn't have any anisotropy. If that's the case, this must be 0. There is no third order anisotropic tensor. This must be 0, and we are only left with these as potential non-linear, linear relationships. We put these, so kappa must be, for fluids, is only a coefficient, the thermal coefficient, and for the this fourth order tensor, again, must be a combination of these identity tensors, and if you substitute it into the relationship for TKL and DKL, we only get 2 independent coefficients coming out. These are Lamè's constant. So here I have Navier-Stokes equations. And you say, yeah, big deal. I knew that already. Okay, yeah, I admit. But I'm happy that I derived it without having to assume it. And Whether it's really modeled your material, that's a different question. If you can tell me and say, yeah, but I have a, I don't know, being pump fluid. Now, okay, we go back to the equations we had there. What is it of those independent variables that are missing there that is really causing effects in your system? We have to add them there. There is more that you can get from the entropy inequality. Those are restrictions on this lambda and mu, because remember, we still have the residual entropy inequality. I think I have it here. I have to go back. Where is it? I'm sorry. Yeah, we still have the residual entropy inequality. So the linear relationship we propose for Q and TKL, we substitute in here, and that still has to be satisfied. And if you do that, you find these restrictions on lambda and, oh yeah, there's the residual entropy inequality with this linear relationship inserted, and that will tell you mu must be positive and 2 mu plus 3 lambda must be bigger than 0. That derives from the fact that otherwise this can be non-negative. That ensures that it's always, and kappa must be positive. Okay? And if you put all these together, now then you get Navier-Stokes equation. You know that. Is that
Great.
any question? Now, once again, to me, the added value is that when I go to porous media, because then I don't have Navier-Stokes equation. And for saturated porous media, okay, I have Darcy's law. But how about multiphase flow? When do I have interfaces? How do I put those into my balance laws, into the constitutive theory? And that's, I think, the interesting part. By the way, if you want to play with this at home, then you could develop the thermodynamics of viscous elastic fluid. Now, for viscous elastic fluid, you have to have a dependence of not only on DKL, but also on the deformation. And if you do that, you see what is it you get now. Then you get these kinds of things that the stress tensor has a viscous part, but also has an elastic part. And then you can go through the whole procedure.
Yeah, when you apply these formulas to porous media, you obtain Darcy's law?
Only for single phase flow.
Single phase flow.
Yeah, because for multi-phase flow, I have all these interfaces that come into play. And I'll go through that.
Another important point in this formulas is to identify what are the variables playing a role in the constitutive equations.
Yeah, so in a porous medium, at the macro scale, I have a continuum, let's say just single phase flow. I have a continuum, and in this continuum, at every point, I have density of fluid, motion of the solid phase, the displacements and motion, and I have porosity, because porosity is a state variable for a. Those are the only three things. So my constitutive equations must be a function of motion of solid, density of fluid, and temperature, temperature. These four things, at any given point, the constitutive function must be a function of those of all points and all past times. Now, I go through the whole procedure again and do the development, say, Taylor series expansion, identify some lower order terms, and I keep them. And to derive Darcy's law, you will see, I mentioned that, we had a discussion the day before yesterday, that you must assume that the fluid is inviscid at Darcy scale, and the fluid is inviscid. The solid, if it is deformable, now we can then assume elastic or whatever. But a porous medium is actually viscoelastic. Viscosity of the, you could, I mean, not that it is, it could, depending on the.
And the type of structure, you have the the randomness in the distribution of the poles is considered, in which variable is considered?
No, it's not included.
It's not included.
No. So at least at the macro scale, we don't have any information related to how the porosity distribution. You could, but it's not in the conservation laws. But one could maybe put in the second gradient of porosity.
No,
maybe
it's
there's
not,
something
it's
there.
not in the conservation laws, perhaps it's in the boundary conditions.
You can't do that. Yeah.
Maybe.
It would be nice to talk about that together.
You didn't mention the name Curie principle, but I expect that that is the arguments behind the zero of the K, LM, and on one of the slides back.
That I must say I'm not familiar with that principle.
You're not?
No, I'm
But
sorry.
let us go back.
He only used isotropy.
Okay.
So he did not use time reversal invariance.
No, but I mean the lack of coupling between tensors and vectors.
Yeah, but that's isotropy. That's not
Is that what you mean by
Onsager.
Yeah.
Oh, I see. Yeah.
No,
yeah.
it's not Onsager.
Oh, do you mean it's
was
Onsager
relation?
Curie.
No, I don't know that one.
Yeah. You take the tensors to be isotropic.
For fluids,
For
we did
instance, the
indeed.
heat conductivity tensor,
Yeah.
you take isotropic and it becomes a constant. And
Right.
so that means that, you know, the off-diagonal coefficients are zero.
Yeah.
Yeah.
And
Which
they-
you did. So if you go back a few
For fluids only. For solid, I don't assume that actually.
Yeah, sure, but still for a solid, then you need Onsager to make the tensor symmetric.
No, the tensor is the tensor. It doesn't have to be symmetric indeed. It doesn't require. It's not required here. You have to make extra assumptions.
You have to
That's
use
correct.
Onsager to
Yeah.
prove that.
That's correct.
Yeah.
Where did you want to go?
I think it is further down.
Was that related to fluid or solid?
Fluid.
And
Here, 57.
okay.
And the next one. Because here, the next one. So no, 57. It was.
Oh, I'm sorry.
This one, yeah. The top equation condition.
Yeah,
That is what I would relate to the Curie principle.
I see. But for a fluid, we really don't know of any fluid. Some crystal liquids maybe that will have preference the behavior of the material. For example, the stress tensor, say Newton's law of viscosity. It's not different in different directions. It's direction independent.
Yeah.
If that is the case, that means the fluid is fully isotropic. And therefore there is no third rank tensor that's isotropic. It doesn't exist. We only have even order tensors that are isotropic.
Well, that's the same as the Curie principle in this particular case. Yeah.
Yeah.
All right, then, no, I guess for fluids that I know, this is not. Any other question? No? Okay, then I think we are meeting at 1.
Also here, yeah.
Yeah.